So last time we talked about matrix multiplication being very closely related to the composition of linear transformations. In this video, I'd like to give just a little bit of intuition about kernel and image. And I like to see them as subspaces, because they are. And I think it helps to just draw a few pictures, maybe. So suppose I have like some kind of a linear transformation that's given by the matrix A equals, I'm going to make some numbers up here, but let's just say 1, 0, 0 maps to 2, 0, 0. So essentially, we'll just stretch everything in the x direction by double. Maybe the y-axis I'll send to 0. And maybe the z-axis I'll map to, 1, 0, 3 or something. Okay. So the way I like to see any linear transformation is I break it down into its dimensions, right? So let's just say that this transformation is t of x equals ax. So t is going from R3 to R3. We're considering three-dimensional vectors to three-dimensional vectors here. And the map is by this matrix. So there's three dimensions to work with, the x and the y and the z. And this map, for each dimension in my domain, the map either sends that dimension to 0 or it doesn't, right? There's only ever those two options for each dimension. So let's just see what it does. Well, maybe here's my domain space R3. I said that the x-axis, everything is being doubled, because this 2, 0, 0 here means that the vector in the x direction of length 1 is being sent to 2. So everything in the x-axis is going to get doubled. So in a way, that is sort of staying the same. Everything just gets stretched out by 2, So that's still going to be there. But how about the y-axis? I'm saying that to 0. So actually, if I call, let's say, this x and this y and this z, the y-axis is going to be no longer there. It got sent to 0. So it's like, it's gone. Everything in that axis got shrunk to 0. And how about z? Well, z, it's 1, 0, 3 now. So everything in the z direction got mapped to, it has some x component, but it's mostly like a z component. So maybe I'll visualize it as something like this, maybe. And sort of you see that at the end of the transformation, I started with 3 full dimensions, but the image of it sort of only got 2 dimensions. It's a plane. Like a 3-dimensional space got sent to a plane that sort of runs in the xz plane. Right? So this is x, and z is still here somewhere. But really, my space is a plane. It's going to be the whole xz plane. The important intuition is that the y-axis disappeared. The set of everything that disappeared, all the inputs that disappeared, that's the kernel. So in a way, the kernel of this transformation is the set of everything, set of all inputs, really, so set of all domain elements that got sent to 0. And it's going to be everything on the y-axis. So, I can almost think of it as just like a whole line. A whole axis got sent to 0. And in this case, it's the y-axis. And then the image is essentially what's left, right? If that dimension got sent to 0, the y dimension, then everything else didn't, then wherever that went, then that's the image. So then the image of t, it's going to be whatever is left over that's sort of mapped by the x and the z axis. So in this case, it will turn out to be the whole xz axis. Because with 2, 0, 0 and 1, 0, 3, it turns out I can hit every vector in the xz plane. It's the xz axis, and the xz axis has got 2 dimensions, right? We discussed that. And so notice here that it all adds up because it has to, in the sense that the number of dimensions that got sent to 0 plus the number of dimensions that were left over have to add up to however many dimensions were originally there. It almost seems obvious once done this way. If a dimension was sent to 0, it's in the kernel. If it's not, then it's got to be in the image. This is the dimension theorem, saying that the dimension of the starting space, which we can call V, this is the domain vector space, the number of dimensions in it, which in our case was 3, R3, well, it has to equal the dimension of the kernel, the number of dimensions sent to 0, the dimensions sent to 0, plus the number of dimensions that were left over and sent to the image. This is dimensions of what's left. So, I see the dimension theorem as intuitively as just this obvious consequence, where if you are a linear map, then of all the dimensions that you start with, you have the ones that get sent to 0, the kernel, and the ones that don't. And it has to add up, because every dimension has to go somewhere. And this is the rank nullity theorem, or the dimension theorem, because the dimension of the kernel itself gets to be called the nullity of T. I guess I have to give it a name. And the dimension of the image of T, the number of dimensions in the image, this is called the rank of T. So this is also called the rank nullity theorem for that reason. Okay. So, yeah, I guess we'll do one last example to finish this video off. Let's have a different matrix, maybe a bigger one. Let's have A, B. Oh, let's see, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, and we'll say 0, 0, 3, 0. A little simpler since we have a 4x4 here. So let's try to find the kernel and the image and verify that the dimension theorem works out. Okay, so we're starting in a 4-dimensional space, which I cannot draw, but I'll try. We'll have x here, y here, z here, and we're aliens. Maybe this is like the next axis. Maybe we'll call it, call it a time axis or something. Who knows? Okay, so let's interpret this transformation. The vector of length 1, the x direction, got sent to the vector of length 1 in the y direction, because this is 0, 1, 0, 0. This is the y-axis here. X, y, z, t, just to make them clear. So, under this transformation t, the x-axis became the y-axis. So I guess I can sort of add this here at the x-axis, same as the y here. And the y-axis has become the x-axis, because this is 1, 0, 0, 0. Okay, so that I made pretty easy. But the z-axis got sent to 0. So all this height collapsed down to nothing. And lastly, the time axis got sent to 3 times the vector of length 1 in the z direction. So the time axis has become the z-axis, and everything got stretched by 3. So, this is the new time axis now. Everything is stretched by 3. So let's just see what happened here. I had 4 dimensions to start with. So the dimension of my starting space, R4, is 4. And what's my kernel? What got sent to nothing? Well, the z-axis got shrunk to nothing. So the dimension of my kernel of t, that's 1. Oop, you can't see, there you go. And the kernel of t, it was precisely the z-axis. It was 1. Well, then what's left over? The x and y and t axes are still there in the image. Yeah, I moved around a little bit. And if you're a linear map, and that can happen. But I still got these 3 dimensions left over. So the dimension of the image of T is 3. And what is the image of T? It's just going to be this 3-dimensional space that's outlined by this new x-axis, that new y-axis, and that new t-axis. So essentially, it's just R3. And we can say that z-axis is just one version of R. R3 in this case is like the x, y, t, plane. X, y, t. Well, I guess it's more like a cube then, a space, whatever you want to call it. And that's another example here. And we can see that the dimension theorem does work out, because it has to. If the z-axis got sent to nothing, and the other 3 got sent to this mismatched axis coordinate, then that's reflected in the dimension theorem here. And just to be clear, when I said the kernel of T is R, yes, it's not specifying what axis it is, but generally we don't care so much about that. The kernel is just a set of real numbers. It happened to be the ones along the z-axis originally, but it's just a set of real numbers. Similarly, when I said the image of T is R3, this R3 is in the image space. Yes, it is technically the new x, y, t axes that got mismatched a little bit, but it's just a copy of R3. And usually we're happy with just writing it that way. But to be clear, this R is from the domain space, because kernel is a set of input elements. It's a set of domain elements. And this R3 is from the image. It's a set of outputs. Okay. Oh, right, and then the last thing I wanted to mention in this video is to formalize why we can think of kernel and image as a true subspace or a true vector space, and what I even mean by that. So, we say that a set of vectors W from a parent vector space V is a subspace if for all vectors x, y, and w and scalars C, then Cx plus y is in W. And really what this is saying is I can scale any vectors in W and add them together any which way I want, I'm still in the space, right? But if you think about it, that's just exactly how lines and planes work in the first place. If I have W to be, let's say, R, the set of real numbers, which is essentially a line in space, well, it's very obvious that if I take any 2 vectors on R, any 2 vectors on this line, I can scale them however I like, make them longer or shorter, I can add them together, but they're still going to be on that line. So the fact that I can do this scaling and adding and remain in the space, that's what makes something a subspace. And you can imagine it works in higher dimensional space well. If I have W equals R2, 2-dimensional space, well, it's intuitively obvious. If I take any 2 vectors here, I can scale them by any C. I can add 2 vectors here anywhere I want. I'm still going to stay as a vector in the plane, still in R2. So really, when you think of subspace, just think of lines, planes, and then higher dimensional planes. And it makes the idea intuitive of why scaling and adding will keep me in that space. Kernels and images are just like that. They are also subspaces to be thought of as lines and planes, as we saw in our 2 previous examples. And to formalize why, let's go prove that the kernel of T is a subspace of the parent domain space V, where T is a map from V to some codomain W, and T is a linear transformation. Right. That is, if T is a linear map from V to W, where these 2 are just sets of vectors, then the kernel of T, which is, recall, the set of vectors that get sent to 0, that is a subspace. And we'll just follow this definition up here. So let C be a scalar arbitrary, and just take 2 arbitrary vectors from the kernel. I would like to prove that Cx plus y is also in the kernel. Okay, well, let's just write what we know. X, y are in the kernel of T. Well, that implies that T of x is 0 and T of y is 0. That's what it means to be in the kernel. I get set to 0. But then, let's consider T of Cx plus y. Since I want to show that Cx plus y is in the kernel, I would like to know that T sends that combination to 0. Well, by linearity, because recall T was a linear map, I can sort of split this up into Ct of x plus T of y. This is by linearity. But we know that T of x and T of y are both 0. There's just C0 plus 0, which is 0. So we've shown that T of Cx plus y is 0. Therefore, by definition of kernel, Cx plus y is in the kernel, which completes the proof. That's what we need to show that the kernel of T is a subspace. So this is just writing out the, proving formally the intuition we had. Okay. And lastly, we'll prove that the image is a subspace of the codomain. Okay. So lastly, we'll prove that the image of T is a subspace of the codomain W, where TV to W is linear. And it follows the same pattern. Again, let C scalar and let x, y be arbitrary vectors from the image of T. Okay. Just so there's no confusion, right? Before in the kernel, x, y were in the domain space. But now, since they're from the image, x and y are in the codomain. Okay. Again, we'd like to show that Cx plus y is also in the image. But what does it mean for x, y to be in the image? Then there existed some vectors that map to them. So there existed vectors, let's say v1, v2, in my domain V, such that T of v1 is x, so something mapped to x, we'll say it was v1, and something mapped to y, we'll say it was v2. Then, well, let's consider T of CV1 plus V2. Because V1 and V2 are inputs, and I can scale them just the same. And let's see what T maps that to. Again, by linearity, I can separate them out. There's a CT of V1 plus T of V2. This is by linearity. But T of V1, well, we said that that's x. And T of V2 is y. This is just Cx plus y. So what have we done with all this? Well, CV1 plus V2 is something that T mapped to Cx plus y. And because V is a vector space, then this combination, CV1 plus V2, will also be in V. So since V is a vector space, CV1 plus V2 is also in V. So this thing in V got sent by T to Cx plus y. That's exactly what it means for Cx plus y to be in the image of T. And the thing that mapped to it was this element CV1 plus V2 in V. Okay. So there we go. We have formally proved that the kernel and image are indeed are indeed subspaces. And therefore, we have proved the intuition we have. We can think of kernel and image as just dimensions. And if you are a domain space, and the stuff that gets sent to 0 is your kernel, and it's going to be a line or a plane or a higher dimensional plane. And whatever plane or line is left over, that stuff gets sent to the image.